Hello, my name is Walid. I'm a PhD student at UMass Amherst working on green and sustainable computing. This is a summary of our paper, CarbonScaler, leveraging cloud workload elasticity for optimizing carbon efficiency. ICT is one of the biggest carbon emitters, contributing almost 4% of global carbon emissions, surpassing the aviation industry. The computing demand is not slowing down. A recent estimate states that computing energy demand in the Dominion electricity grid, where many data centers are hosted, will exhibit a 3.6x increase by 2028. Although adopting renewable and carbon-free energy sources greatly decreases computing operational emissions, a carbon-free electricity grid is decades away. So the solution is to directly minimize the carbon footprint of computing by shifting workloads based on the availability of clean energy, known as carbon-aware scheduling. So as the energy mix varies throughout the day, the carbon intensity changes as well. One way to exploit this variation is to, instead of running batch workloads immediately in a carbon agnostic manner, the scheduler can execute the job when carbon intensity is low and pause it otherwise, known as temporal shifting. However, this highly increases the job completion time. Another issue is that this method fails to exploit the variations by using the same execution rate aside from the carbon intensity magnitude. So in this paper, we use a different approach. When carbon intensity is low, we run the job at a higher rate by scaling the resource allocation. We consider the carbon intensity variation by running at a higher scale when carbon intensity is lower. However, scaling jobs often lead to sublinear speedups, which must be considered in the scaling decisions. The key idea to solve this problem is by formulating it as a marginal resource allocation problem where greedy solutions are optimal. The algorithm computes the schedule by greedily selecting the scale and time when marginal capacity per unit carbon is maximum. Check out the paper for more details about the algorithm and its optimality. This slide shows the results across 4 workloads using Ontario carbon intensity trace. The workloads are 2 MPI applications and 2 ML applications. We assume that all jobs are 24 hours and all jobs must finish within these 24 hours. The graph shows carbon emissions where lower is better. As shown, the emissions differ based on the resources, as GPUs used for ML applications consume more energy than CPUs. However, in both cases, CarbonScaler reduces emissions by 50%. Another factor for the reduction is the scalability. For instance, low or non-scalable jobs cannot benefit from scaling. Finally, we show that using a static scale factor might not work for all workloads and might increase the emissions, as seen in the ML VGG application. So the takeaway is that CarbonScaler can reduce carbon emissions without increasing the completion time. In this paper, we presented a new approach to carbon-aware batch scheduling. We proposed the CarbonScaler algorithm, an optimal greedy algorithm for the carbon scaling problem. We evaluated the efficacy of CarbonScaler using Kubernetes implementation and trace-driven simulation. Come to our talk in session 4A, Sustainable Computing, to know more about the paper. Thank you.